but they're manageable. There's just a process to it. All right. So we're going to skip over page 48 and go right to geometric applications of optimization. And like I mentioned in the beginning of the class, but I also mentioned last time, if we don't go over a particular type of problem, it's because that particular type of problem is not something that you would be expected to do on an assessment. All right. So I mentioned this definitely last time. I kind of went a little crazy with just putting every problem I could find, like in creation, into this packet, and it's way more than we actually need, including the business ones. The business ones are more, honestly, they're for my business calc class, not for this class. All right, so the process. Define the variables, write a primary equation, use the other information to write a secondary equation that relates to variables used in the primary equation. Okay. The step 3 varies from problem to problem to the point where that step is almost like unnecessarily complicated. And you'll kind of see as you get into some of the examples under what circumstances you need a secondary equation and what circumstances you don't. Find a feasible domain. Feasible and practical domain mean the same thing. So for example, if we're talking about areas, we probably don't need negative dimensions. Okay, so just kind of keep that in mind. Find extrema. Okay, that's step 5, words to that effect. And then interpret the solution and clearly indicate your final answer. All right, so that part is the verbal response. It's like you give me the answer, it's a word problem. I'm giving you the question in words, you give me the answer in words. I mean, I think that part is pretty straightforward. Okay, so number 1, very simple problem. And in fact, it can be done without calculus, which is why we're doing it first. We do something that we probably already know the answer to, but we want to learn the calculus approach for it. So Jack wants to create a rectangular garden. He has 100 feet of fencing available to make the border. What are the dimensions of the plot with the largest area? It's the largest area. All right, so we want to optimize area. All right, so optimization, I mean, it's written right here. They're applied maximum and minimum problems. When we optimize is just an umbrella word for maximum and minimum, most and least, best and worst, So we're looking at any instance in which we're trying to optimize as a case where we're trying to find a maximum or a minimum. All right. So they're asking us to find the largest area. So it's the area formula, the area model that we want to optimize. All right. Now they say it's a rectangular garden. So that's telling me I want the area of a rectangle, which is length times width or base times height, whatever you like. All right. Now I know I say define variables, but sometimes the variables are so common sense that you don't really need to. I mean, most people can look at A equals LW and know that A means area, L equals length, and W equals width. Right? You don't need to write let L equal length and so on. It's if you're using other variables that you would want to define. All right. So if for some reason you decided instead of using A equals L times W, you decided to use f of x is equal to x times y, like that, you probably should define some things there. Right? Even that wouldn't make perfect sense right away. Okay. So I'm going to draw a rectangle. Generally, for rectangles, it's just like related rates. Not like you need to draw a rectangle to visualize a rectangle, but let me just do it real quick anyway. So I want to optimize area, but they tell us that we have 100 feet of fencing. That's a measure of perimeter. So they told us the perimeter, and they want us to determine the area. All right. Now, perimeter for a rectangle is 2L plus 2W. So in this situation, since we know the perimeter is 100, we know 100 is going to be equal to 2L plus 2W. Common factor of 2 divided out, 50 is equal to L plus W. I can solve for one of these variables in terms of the other, because I'm looking at A equals LW, and I'm seeing two variables. If I compare this down to just a single variable, that's a pretty good place to be, right? Because then it's going to make it a whole lot easier to differentiate. I won't have to use like implicit differentiation, right? So I'm going to solve this for, it doesn't matter what you solve it for, because it's saying what are the dimensions. I need them both eventually. I'll solve it for L. So L is equal to 50 minus W. So now what I can do is perform a substitution, replacing the L in my area formula with 50 minus W. So A would be equal to 50 minus W times W. All right. Now that A is really A of W, because now it's a function of W. All right. Now I can differentiate this, but I kind of want to distribute it out first because it'll make the differentiation process a little bit easier. So A of W would be 50 W minus W squared. So to find the derivative, it's just simple power rule. So A prime of W would be 50 minus 2W. All right. So the question becomes, it's a natural question. Well, I want to take the derivative, but why would I want to take the derivative? Well, I want to optimize. All right. So if I'm optimizing, I'm looking for a relative max, a relative min, or an absolute max or an absolute min. The only way I'd have an absolute max or an absolute min is if I was given a restricted domain, or I can infer a restricted domain. That doesn't seem to be the case here, but I can find critical values and then use those critical values to determine extrema. All right, so I would take my first derivative, set it equal to 0, and solve, because there's no reason why we would set it equal to 1 over 0, because it's another polynomial function. So 2W would equal 50, which would make W equal to 25. That would be my critical value. So now it's a question, yeah, okay, it's a critical value. It could be a relative max or a relative min. We only have the one critical value, so it's probably a relative max, but we don't really know until we test it out, right? So when it comes to areas, we tend to want to work with only positive values. So I'd make a little sign chart here. That sign chart is going to involve the independent variable W. And that width, I suppose it could be equal to 0, but then it really wouldn't be a rectangle. So I would want to make it greater than 0. Go up to 25. Then stop at 25. And then go from 25 to some reasonably large value. That's the find a feasible domain for the function you wrote in step 3 part, right? Because looking at this, well, that function, that polynomial function is infinite. It can go on forever. W could be anything, but a feasible domain. Well, I don't want W to be negative, and I probably don't want it to be too big. I suppose it could never be as big as 100, because that's the amount of perimeter I have available. And in fact, it wouldn't even be as big as 50, because you have two W's in this perimeter function. If each one is equal to 50, then all of your perimeter is accounted for just by the width, and we would have no length. So I would max it out at 50. All right. And so that would be the feasible domain. And then from there, I would evaluate my first derivative and see whether it's increasing or decreasing, and then draw an appropriate conclusion. All right. So into my first derivative, I put some value between 0 and 25, nice convenient value like 10. If I put a 10 in there into my first derivative function, 50 minus 20, positive number. Doesn't matter what the positive number is, as long as it's positive, it's going to give us an increasing value. All right. Pick a number between 25 and 50. So for example, 30, put it in a 30, negative 2 times 30 is negative 60, 50 minus 60 is negative 10. Bottom line, it's negative, shows that it's decreasing after that critical value. Increasing followed by decreasing indicates a relative max. So that X value, the W value is the location of a relative maximum, right? So they said find the dimensions. What are the dimensions of the plot with the largest area? All right. Well, I got one of them. I know that one of the dimensions is 25, the width. Now I just need the length that goes along with that. So take my perimeter function, or at least my modified one. We had this, we did 100 equals 2L plus 2W. We simplified. Along the way, we came up with L equals 50 minus W. So that's the relationship between length and width. 50 minus the width, which we just discovered, is equal to 25. It's going to give us the length, which is also 25. So the dimensions are length times width, so 25 by 25. The units are feet, so 25 feet by 25 feet. All right. Again, what are the dimensions of the plot with the largest area that can be enclosed with this fence? It didn't say what would be the area, but if you wanted to figure out the area now, the length and width, that would be easy enough. Right? So that wouldn't be, it's 625 square feet. You just multiply. All right. But it's not terrible. But there is that part where, it's basically what we were doing before, except you have to come up with the equation first. Like, for example, number 2, let's check the chat. Okay. So number 2, find two positive numbers whose product is 192. All right. So this is probably an instance where I would use a let statement. Although, in all honesty, when I write X and Y, and the statement says two positive numbers, it's probably common sense that one of them is the X, X is one of them and Y is the other. But, just for clarity, I would say let X equal one positive number and Y equal the other positive number. Say the first, the second, whatever. Product is 192. Whose sum is a minimum. So that's what I'm looking to optimize. All right. I'm optimizing the sum of the two numbers. All right. So I would actually throw in another component of my let statement here. I'd let S equal the sum of the two numbers, sum of the numbers. And I could actually make a very simple equation out of that. S equals X plus Y. All right. This is the one that I'm looking to optimize. So I want to substitute into that formula. All right. It's an equation that involves two variables, X and Y. I want to swap out one of those variables if I can, and I can, I'll solve that first equation here, the xy equals 192. I'll solve that for y in terms of x. So divide out the x, and you get y is equal to 192 over x. Yeah, that's true, but I'm just kind of looking ahead. I'm going to write that as 192 x to the negative first. All right, looking ahead, I know I'm going to be finding a derivative. When I find a derivative, ideally, I'd like to be using the power rule. If I'm using the power rule, I probably want to have my function written as a power function. All right, so by writing it like this, I can make a nice even swap, and I would get s of x, now it's a function of x, is equal to x plus 192 x to the negative first. And now the derivative is going to be really, really easy to compute. All right, so s prime would be 1 minus 192 x to the negative second. All right. But now that I took the time to get it in that nice convenient form to find the derivative, I need to take that derivative and set it equal to 0 and set it equal to 1 over 0, if applicable. So what I'll do is I'm going to put that back in the a nicer form. S prime of x would be the same as 1 minus 192 over x squared. All right. So setting that equal to 0, setting that equal to 1 over 0. Now you can see, hopefully, that procedurally, there's not much difference between this question and the previous one. We have a different function that we needed to differentiate. We came about that function in a completely different way, but we're still going to take the derivative. We're still going to find critical values. We're still going to make a sign chart to determine the nature of those critical values, and then we're going to draw a conclusion based off it. It just makes life easier if you recognize that trend that exists in these kind of problems, because it is pretty consistent and manageable, really. And so the only thing that ends up becoming an issue, as is the case with all word problems, is where does the equation come from? Once you get the equation, everything else will be pretty by the book. All right. So common denominator. So multiply top and bottom of the 1 by x squared. And you get x squared minus 192 over x squared. All right, and so 1 over 0 would be equal to the same thing. Cross multiply. That 0 is the same as 0 over 1. So x squared minus 192 would be equal to 0. Cross multiply, you get x squared is equal to 0, which we're going to pretty much immediately disregard, because when I solve this one, set it equal to 0, they said two positive numbers. X is one of the numbers. 0 is not, it's not a positive number. It's not a negative number either. Irrelevant, right? It also happens to be the location of an asymptote based off of this equation. But, that's kind of besides the point at this point. Contextually, we eliminated it from being a possible solution. Right? And that kind of overrides any of the math that would go into play. So add the 192 to both sides, and you get x squared is equal to 192, making x equal to plus or minus the root of 192. But again, I only want positive values because of the way the question was framed. So I'm going to disregard the negative and just say the square root of 192. So yeah, I would have a critical value at negative the square root of 192, but that's beyond the context of the problem. I only want positive values. So when I make my sign chart, I'm going to do pretty much what I did in the last problem. And that is started off at 0. Go to the first critical value, first and only critical value. Stop at that first and only critical value. Yeah, that radical could probably be simplified, or maybe not. It doesn't really matter at this point, because I'm really just looking to evaluate it first. And then radical 192 going on to some reasonably large value. All right. But the context of the situation will give us an indication of what defines reasonable. All right. So the product has to be 192. So they're positive numbers. I mean, I suppose that it's possible that I can multiply 2 positive numbers and get 192, and one of those numbers would be 192. 192 times 1 will do the trick. All right. You could also, if you multiply by some decimal values, you could even go beyond 192. But at this point, I would say 192 is a reasonable high point, and we wouldn't really need to go beyond that. Right? We just need to have some endpoint beyond the 192, because it's beyond the radical 192, because it's the radical 192 that we care about. Right? So as long as you don't put something absurd as your high point here, you're going to be okay through your high value. Like, as long as you don't put like infinity, right? I mean, contextually that wouldn't make sense, because we're looking for 2 positive numbers. Yeah, infinity is technically the representation of a number, but it's not a finite value, and we're looking for a finite value. And so basically, as long as you don't put infinity, you're going to be okay. All right. Now our function here, we call that S prime. Well, we called it S, but S prime is what our derivative amounts to. We draw a conclusion here. So we would pop a value between 0 and radical 192 into our derivative function. All right, you can do that technologically, or you can do it in your head, whatever makes sense. I'm just going to do it on tech here, because numbers are kind of weird. But if you put in something like, 10, for example, you're going to be looking at something, 192 over 100 is going to be something that's bigger than 1. So 1 minus something bigger than 1 would be negative, but maybe you don't see that. So I'll just do it manually. You see negative value. And then something that we know is bigger than the square root of 192. So the square root of 198, like 192, you're living in the 14 to 15 range, because 14 might even be high, but something in the mid-teens. So as long as you go beyond that, like 20, for example, you'll be okay. What we just need to show is that it's going from decreasing to increasing. And the reason we need to show that is because it's saying the sum has to be a minimum. A relative minimum happens over an interval that's decreasing followed by increasing. So a decreasing function followed by an increasing function gives a relative minimum. So based on the framing of the question, we kind of already have an idea of where we're going with this. We just needed to kind of get there. All right. So then instead find 2 positive numbers. One of those numbers we now know is radical 192. The y value, just kind of taking the most convenient representation of y being equal to 192 over x. If x is equal to the square root of 192, 192 divided by the square root of 192 is also the square root of 192. So as it turns out, they're both the square root of 192. All right, so the question is, why the domain start at 0, not 1? Oh, because technically it could still be a decimal value. You could have a positive number like a half, for example. It ended up not mattering, but let's say you had 1/2 as one of the values, then you could still get to a 192 through a product. 192 divided by 0.5 would be 384. So the two values could be 0.5 and 384. You know, you could still have decimal values. All right, so those numbers between 0 and 1 would still technically be part of the fund. But like I said before, capping it off at 192 was kind of an arbitrary decision because we could still go further. Because if you can get infinitesimally close to 0, then you can get really, really close to infinity also. So you can go, if you can get down close to 0, then you can go really, really big on the high side. You gotta cap it somewhere. As long as you have some reasonable values around the relative extrema, then you're good to go. Okay. So one last one. The manufacturer wants to design an open box. This is a classic question. Open box having a square base and a surface area of 108 square inches. What dimensions will produce a box of maximum volume? All right, so we're looking to optimize volume, and that box is rectangular. So volume, length times width times height. Now, I did say it's a square base. All right, so square base, so that's a good piece of information there. All right, so if I'm drawing my box, which I always struggle with, I'll just try to do it real quick. Yep, already filled. Yeah, it wants to lock in at that angle. I could always do it. I just got to do a construction style. Even that doesn't look so hot. Oh, I hate when that happens. Because I had it like a straight pinky. All right, close enough. Best I can do. All right, so this is my box. It has a square base, so we know length times width times height. But they're saying that the base is square, which means that this length here is the same as that length there. So L is equal to W. So we could actually refine our volume formula to make that substitution. We could say L times H, or we could say W times H. It really doesn't make a difference, whichever you prefer, right? They did say that there's a surface area of 108 square inches. Now, this one is an open box, so it doesn't have a top to it. All right. So the surface area, when we're talking about a rectangular figure, or at least three-dimensional one, we'd have to incorporate every facet into this area. So we'd be looking at the area of the base. And so at this point, we kind of have to make a decision. Are we going LL or WW? WW sounds more fun. So that's what I would do. I'd let this be W. W by W would give me the base, so W squared. Then each side would have a dimension of W and a dimension of H, no matter which side you're dealing with. All right. So W by H, another W by H here and here. If you do the opposite sides, it would be the same stuff. The back side here, this other sidewall. So in the end, you'd actually have 4 of those WHs. We don't care about the top. They said it's an open box. A rectangular solid has 6 sides. If I'm disregarding one of them, I should have 5 sides. I have 4 of the WHs and 1 side valued at W squared. That's 5 sides accounted for. So we're in good shape here. Okay. So that's one of my equations. Since I'm looking to maximize volume, what I'd want to do is use this equation to help me swap out a variable in my volume form. So volume, we would say, is normally W squared H, but I do know that the area is 108 square inches. So I could say 108 is equal to W squared plus 4WH. So at this point, I can swap out an H for a W or a W for an H, again, in the volume formula. That's what we care about. It's just a question of which one. And that is, in my mind, determined based off of the nature of the other equation, the area equation, right? You kind of, I missed an H. You look at it and say, well, which one of these variables is it going to be easier to solve for? I only see one H. A second ago, I didn't see any H's. But it's going to be easier to solve for H here. If I subtract the W squared, you get 108 minus W squared is equal to 4WH. Then I could just divide out the 4W. And now I have H all by itself, and I could use that to sub into the other equation for H. So my volume formula, which would now be V of W, would be W squared times, instead of just the letter H, it's what H really is in terms of W, which would be 108 minus W squared over 4W. All right. So looking at this, it's like, oh, I got to differentiate this. This is going to be product rule, quotient rule. It's going to be a nightmare. Maybe do a little algebra first. All right. W goes into W squared, W times. Distribute that W. So we would have 108 W minus W cubed over 4. Break up that fraction. (108) divided by 4, well, that's 108 divided by 2, divided by 2 again. 108 divided by 2 is 54. Divided by 2 again is 27. So 27W minus 1/4 W cubed. So taking a little time in the early going to simplify your equation, well, in this case, expression, makes it so much easier to find the derivative. So V prime is going to be 27 minus 3/4 W squared. I don't have to worry about setting that equal to 1 over 0 because this is a polynomial function and polynomial functions are never undefined. Right, so I would solve this by adding 3/4 W to both sides. Sorry, 3/4 W squared. Multiply both sides by 4/3. Makes it W squared on the left and 36 on the right. I mean, after all this mess, for it to be so nice. I mean, that's pretty surprising, I think. You get W is equal to positive or negative 6, but our critical value is just going to be W equals 6 because we're talking about the width of a three-dimensional geometric figure. Right? The three-dimensional part is not as relevant as the fact that it's geometric. All right. So we're not concerned about a negative width. All right. So then a little sign chart. We know some surface areas and stuff like that, but we are ultimately talking about the width of a figure. All right. It crashes. And I open it back up. It says that it's optimizing, which is really just so poetic. Oh, no, it doesn't say optimizing anymore. Just preparing it for a faster experience. It used to say optimizing it for a faster experience. Maybe it doesn't believe that the users have the vocabulary to understand what optimizing means. Right, anyway, we don't expect the width to be negative. We don't expect it to be 0. So we would say parentheses on the 0, because it could be a fractional value. Going to 6, stopping at 6, and then going from 6 to some reasonably large value. Right? In terms of something that would be considered reasonable, there, I mean, sky's the limit, but I wouldn't expect it to be longer than the surface area itself. Right? In fact, it's probably not even longer than the cube root of the surface area itself. But oh, sorry, that 1/6 of the surface area. Even that probably wouldn't make sense. Some fraction of the surface area. I'll go with that. So I'm just gonna say 108, just because I don't really have anything better. I was thinking of the 108 as volume there. That's why I said cube root, in case anyone was wondering. So V prime, and then some kind of conclusion. Now, we are looking for a maximum volume. So my expectation is, because we only got the one critical value, if this problem is going to work out, unless it's some kind of trick question, which I would never do on a test, unless it's some kind of trick question, I would expect to get increasing followed by decreasing. Right? We'll see how it plays out. Right? So I have my derivative function right here. If I put in a value between 0 and 6, so let's say I put in the number 1. 1 squared is 1, times -3/4 is -3/4. 27 minus 3/4, that's a positive number. So that shows that it's increasing. Right? Pick a number greater than 6, but less than 108. I mean, I'm raising something to a power of 2, so I'm thinking something substantial, like maybe 10, but also something that's easy to raise to the second power if I'm doing it in my head anyway. So 10 squared, for example, is 100. 3/4 of 100 is 75. 27 minus 75 is definitely a negative number, and so that shows decreasing, which means that we are indeed dealing with a relative max. All right, so it says what dimensions will produce a box of maximum volume. All right, so I need to answer the question that's being asked. I have a width. Now that's great because we know that it's a square base, so that width is happening twice. All right, that's 2 of the 3 dimensions that I need. All right, so I know these are going to be the same. They're both 6. So the height is just going to be whatever I would get when I substitute in to this equation. All right. So let me just snag this bad boy here. You can tell I accidentally used the marker instead of the lasso, possibly. So I'd find h of 6, which is 108 minus 6 squared over 4 times 6. So 108 minus 36 over 24. So 72 over 24, which is going to give you a 3. So my dimensions, square inches for area, so the linear units of measure are inches. So the two base dimensions, length and width, or width and width, or length and length, 6 by 6. So 6 inches by 6 inches by 3 inches. For the height, it only asks for what dimensions would produce a box of maximum volume, and these would then, in fact, be the dimensions that get that. All right. So it's a pretty typical question, pretty typical calculus question for optimization. But the next one is really the big one, the one that comes up in literally every math class you've ever taken and ever will take. So yeah, I'll put a star on number 4, and we'll talk about that next time. But the question that I see here is, wouldn't optimizations always have a relative max? What would you do if you had a relative min? Some questions, like for example, number 2, this could have said find 2 positive numbers whose product is 192 and whose sum is a minimum, or maybe 2 negative numbers whose sum is a minimum. I'm sorry, maximum. It could always go in the reverse, but sometimes it doesn't make sense to go in the reverse. But you'll see a question like number 5. It talks about, I mean, baked beans, of course, but it's a can of baked beans, so it's talking about a cylinder. It's talking about what dimensions would allow for minimum amount of metal to produce the can. So it's asking for us to optimize using a minimum, but the process would be exactly the same, except in our sign chart, we would be looking for a relative minimum instead of a relative maximum. All right. So we would get potentially multiple critical values, and we'd have to parse out which ones correspond with a maximum and which one correspond with a minimum, and then decide which one makes sense in terms of what the question's asking. All right. So it really is more contextual than anything else, because as we've seen, you could have multiple types of extrema in any question or any function. It's just a question of what extreme values apply in what contextual situation. So I'm going to stop the recording.